Welcome to IT Visionaries, created by The Mission, your #1 source for accelerated learning.
90% of the data that exists in the world today was generated in just the last 2 years. And each day, 2.5 quintillion bytes of new data are created. That pace is only going to accelerate. With these skyrocketing volumes of data, how can companies' computers and servers efficiently process it all? Plus, how can they process it all in an energy-efficient way? In this episode, we explore these questions with Alex Wright-Gladstein, CEO and co-founder of Ayar Labs. Ayar Labs has developed new electronic-photonic integrated circuits to move data using light instead of electricity. Prior to founding this company, Alex received an MBA from MIT and was the energy entrepreneurship leader there. She also founded Everyday Science and led energy efficiency programs at Enernoc, the first smart grid company. Get ready to learn about the future of computing with light. Plus, learn how the technology Ayar Labs is building will revolutionize data transfer.
IT Visionaries is brought to you by the Lightning Platform by Salesforce. The Lightning Platform is a leading cloud platform that makes building AI-powered apps faster and easier. With Salesforce, now everyone is empowered to build apps for their organization. Learn more at salesforce.com/buildapps.
Alex, it is so good to have you on the show today.
Thanks so much for having me.
So today we're going to be talking about something really fun, the future of computing. And it's something that I think, whether you're a CIO, CTO, or IT leader, is going to be something really important for the future of your company and really how we look at architecture, infrastructure, and the cloud, networks, all of that. So Alex, could you share a little bit about what you do and the company?
Sure. So I'm the CEO of Ayar Labs, and what we're doing is we're using light to move data in and out of chips instead of electricity, removing the bottleneck in moving data between chips and making computing much faster and more energy efficient.
So it's a pretty simple problem.
It is.
Yeah. We just need to make computing faster and not too tricky. So how did the genesis of the company come about? How did you have this idea? And just kind of tell me the starting of the organization.
Yeah. So, this is a problem that the industry has been aware is going to happen for a long time. And this company was formed out of a 10-year-long DARPA-funded research project. So DARPA is the research arm of the U.S. Department of Defense. They put $20 million into figuring out how do we get past the copper input-output bottleneck that we're going to see 10 years in the future. They started looking at this back in 2008, and they saw that we were going to have this issue around right now and decided to put money into figuring out how to fix it. So they funded this research collaboration between MIT, UC Berkeley, and University of Colorado Boulder. And that group of researchers spent 10 years trying to figure out how do you get light in and out of a processor chip and a memory chip using light. And 10 years later, they made the world's first processor to communicate using light. They actually started working on this in 2005. So in 2015, they made that first processor to communicate.
Oh, wow. So it
using
actually
light.
took 10 years.
It actually took 10 years. And it was a huge breakthrough. It was published in the biggest research journal, Nature, which is a big deal for people in these fields to get published in Nature. And that was also around the time that I met this group. So I got my MBA at MIT. And my background is in clean tech and energy efficiency. I did a lot of work with big data in a prior life. And I went to MIT as an excuse to meet smart people inventing things that could have an impact on preventing climate change. And I was just blown away by this team when I met them. They were just about to demonstrate this world's first processor with optical I/O. And it was just a great team of guys as well that I was excited to get to know. So I convinced them to start the company. And we started it in the same year that they published that research result, 2015.
Wow. So walk me through kind of the last 3 years from founding to where you are now. Like, what were the steps that went into product creation, to launching, to all of that?
So we've made a ton of progress in the past 3 years, really starting with figuring out what do we do with this technology. It was a really cool demonstrator, having a processor that also has a lot of really advanced optical devices on it to be able to communicate using light. And there were a million things we could have done with it, a lot of directions we could have taken the company. So the first step was really just to get to know who our customers should be. And we started by just talking to as many people as we could across as many industries as we could, looking at where this technology could be useful. So we pretty quickly moved the company out to California because Silicon Valley is a place where a lot of chips are getting made, and we figured it was important to be close to our customers and really started to get familiar with the problems that chip makers are starting to face and realized that the original reason that DARPA funded this project has turned out to be a very good reason. The industry is actually right now getting to a point where the roadmaps for hardware that's going into data centers and into supercomputers is reaching the end of the road. Probably most of your listeners have heard of Moore's Law and how successful it's been in increasing the amount of processing power we can fit on a chip exponentially over time. And most people have probably also heard that Moore's Law is running out of steam. And so we're not going to be able to keep growing the amount of processing power we put on chips exponentially moving forward the way we have for the past few decades.
I mean, that's really revolutionary in and of itself, that this law that has been governing the creation of chips for the last 40 years, something like that, that it's kind of coming to a point where this is no longer possible. So why is that?
If you were to ask the manufacturing experts who are making these incredibly complex chips, you would get a much better answer. But from my understanding, it comes down to a couple things. The first one being cost. It is getting so expensive to make transistors tinier and tinier that it's starting to just seem not as worthwhile to as many manufacturers to even try to do it. And then another one is yield. So the tinier your transistors are, the harder it is to get them to work or get a good number of them working on a single chip. And so just getting these manufacturing processes working with such tiny transistors is really, really hard. And that's another reason that more and more manufacturers are deciding this is the end. They're not going to keep going with downsizing moving forward.
So with that kind of being said as the problem, what is the solution to this? I mean, obviously part of the solution is using light, but how does that impact the speed in which we're working? What is the practical application? Is it twice as fast? What is the application of using light?
Yeah, so we're not using light to replace transistors. What's really exciting about what we've done is we've figured out how to use light-based devices alongside electrical transistors. So we're able to leverage the chips that companies like Intel are making to make processors, or NVIDIA are making to make GPUs, for example, and use those super advanced chips alongside our chips, which make it possible to just feed much higher data rates into and out of those chips. So most people are familiar with that exponential scaling of Moore's Law. They're probably less familiar with the parallel improvement that's been happening with how we move data in and out of chips. So we use copper pins to get data in and out of chips. And every few years, the amount of data that we can fit across those copper pins has been doubling. So there is a lot of technology that's gone into being able to double the data rates across these copper pins every few years. And something that's happening right now, alongside the end of Moore's Law, is the end of being able to scale that increase in bandwidth per copper pin. Today, chips can send 25 gigabits per second across a copper pin, and very soon they'll be able to send 50 gigabits per second across a pin that's kind of coming out in the next year. The next generation after that, which is expected around 2021, will be at 100 gigabits per second, so the next doubling on a copper pin, and the industry has all agreed that's the last generation. We'll never be able to increase that data rate again. We've gotten to the physical limit if you're trying to exit a chip package, i.e. just get data in and out of that chip to any useful distance. And so that's what DARPA saw 10 years ago, and that's why they put $20 million into this research. It was to solve that bottleneck problem. Because now we have these chips that are able to process so much data because there's so many transistors packed onto a chip, but you can't get enough data to and from those chips to be able to make use of all that processing power. And so chips are idling a majority of the time, just waiting for data to come and go. And that's hugely wasteful. So What we're offering is a 10x improvement in how much data you get in and out of the chip at a time. And that removes that bottleneck entirely and now makes it possible to fully use the processing power you have and massively increase processing speeds as a result.
So basically, the light replaces the copper in this scenario, that you're sending it 10 times faster using light than copper. I mean, not to turn a phrase here, but I've heard the speed of light is very fast. How do you look at that problem set and say, like, does this make our phones 10 times faster? Like, what is the impact on the end user of this type of speed?
So to understand that, you have to think about the specific applications. It has much more impact where you're moving lots of data around and much less impact where you're not. So, for example, machine learning, AI, especially training for AI, involves a huge amount of data getting moved around between GPUs, CPUs, and memory.
So you're talking about supercomputers that are doing extremely large amounts of data. And
That's
when you
right.
say training for AI, what do you mean that those things are, the actual learning that's going on in the machine uses tons and tons of bandwidth?
That's right. So with machine learning, there are two subsets of what you do in machine learning. First, you train your algorithms by feeding in data sets, and that's how you get the machine to learn. And then inference is the other part where you're using your algorithms to now make predictions. So in training in particular, you have huge amounts of data moving around, and those copper pins are a huge bottleneck even today. And so by increasing how much data you can get in and out of those chips by 10x, you can cut training speed way down. And it depends on the exact architecture you go with, but it could be 10x to 100x decreases in how long it takes to train your algorithms. And right now, data scientists are waiting sometimes a week, sometimes a month for their training sets to run through. And so that can make a huge impact so they can iterate more quickly.
Wow, they're waiting a week to a month for these. I mean, is this something that we're going to look back 20 years from now and be like, people are waiting now an hour for the same amount of time using these types of technologies? I mean, like, is that kind of the difference here, that, machine learning will be able to increase its productivity in that like massive amount of scale?
Yeah, I think really it could even get down to minutes or seconds. Because the cool thing when you use light is you change everything about the limitations of how you design your machine. So when you use electricity to move data between chips, there's a trade-off between how much data you can send and how far you can send it. So right now, people are packing as much processing power as they can into a single server box to get chips as close to each other physically as they can so that they can have high data rate connections between them. When you use light to move data, you don't have that trade-off anymore. Light has very low losses as it travels long distances. That's why it's used for the backbone of our internet infrastructure. That's why we use it to send data across oceans. And so now we're using that technology inside machines, and it means you don't have to pack your processors close to each other to be able to move lots of data between them anymore. So it just means you can scale almost infinitely and bring all that waiting period way down by really leveraging the technology.
So is this going to be a huge competitive advantage for data centers, for government agencies, for cloud vendors? Is that going to be something that really differentiates them going forward? Because if you have this type of technology and you're leveraging light rather than copper, and you can be 10 times faster, and your computing power is 10 times faster, aren't you going to be a much more viable product for other people to use?
Absolutely. And I think that's likely a big reason that the US government has invested so much money in this space and in our technology in particular. Yeah, it'll definitely be a big differentiator, especially with the end of Moore's Law. So in this bigger context, the trends right now in high-performance computing and machine learning are to cram as much processing power as you can on a single chip. And that's worked really well up till now because of the scaling of Moore's Law. But now that we're at the end of that, we're not going to be able to cram more processing power onto single chips. Our technology makes it possible that you don't have to anymore. Now you can have these fat pipes between chips, and you can have a whole data center that operates the way that a single chip operates today.
That's really interesting. So instead of packing more onto each individual chip, you're increasing the ability to flow in between chips because you can't use copper, you're using light. So the ability to use the transfer of information more quickly is actually kind of the extension of Moore's Law, right?
Yeah, it makes Moore's Law less important almost because you don't have those limits in getting data in and out of the chip anymore.
So what are the types of organizations that you're working with now? Like, who are your customers and who are the people who are starting to leverage this technology? And is it launched? Is it in the wild? Is it working? Like, what are the type of things that are working now and that you're seeing now?
We are at a point where we've developed the technology from this really cool demonstrator, this processor communicating with light a few years ago, to where now all the key building blocks for our first product are working. So we're starting to enter qualification and also starting to work with customers to design our product into their products. So you asked, who are our customers? Who are we working with? And they fall into a couple categories. One is folks who are buying high-performance computing machines, whether it's machine learning or more traditional high-performance computing and supercomputing types of folks. Some of them are definitely in the government ecosystem, Department of Defense, Department of Energy, and some of them are private companies that have big needs for processing data. And then the other category is in more general purpose data centers. And in that environment, we're seeing a big shift towards cloud computing. And the vendors of cloud services are really at the forefront of adopting new hardware. So we're also working with those folks to incorporate our technology into their platforms. And then we also work with the folks that are selling hardware into those environments, whether it's into supercomputers or into cloud data centers. So there are companies that sell systems into there, such as HPE, Dell, Cray, IBM. And then there are also the folks making the chips that go into those systems. Like Intel is the most obvious one for a CPU, NVIDIA for a GPU. Broadcom makes switch chips, and all of these folks are at the forefront of the problem of needing to be able to escape more data from their chips. And so we're working directly with them to interface our chips with theirs.
Switching gears a little bit to blockchain and how much computing power it uses, is there applications there? Are you working with that? Are you working with any blockchain companies? Is this something that you're looking at in the future, or is it mum's the word?
I personally am really excited about the future of blockchain and Bitcoin. But this goes back to something I mentioned earlier, which is where this is most useful is where a lot of data is moving around. And so when people ask me, can we use this for Bitcoin mining? The answer is that actually is much more compute heavy than it is data heavy, kind of by the nature of what it is. Proof of work is really all about proving that you have processing resources, processing something. And so my understanding is that we don't have huge volumes of data moving around in Bitcoin mining machines today. Maybe that will change in the future.
Yeah.
I also think that there are some groups starting to talk about using light to do an optical proof of work to save energy there. It's an interesting idea. I don't know too much about it. I think it's very early stage. I think in general, it's a really interesting field and it's just very nascent. So it remains to be seen how optics will help. But at its most basic, our optical I/O uses 10 times less power than electrical I/O does. And so in the data that is moving in and out of Bitcoin mining chips, we can cut down on the energy used for that purpose, which is just a portion of what Bitcoin mining machines are using energy on, but that is a place where we can provide service in terms of just lower power used.
That's really interesting. Could you talk about what this looks like in the next 10 years? Obviously 10 years ago, DARPA said, hey, we want to build this. What do the next 10 years look like? Is this something where 10 years from now, everyone is going to be using this in supercomputing with all the different types of data centers and cloud vendors and all of that? Or is this something that is going to be a slow burn? I mean, I'd imagine that obviously, it taking 10 years to get to this point, but now we're here, right? So I guess just kind of share what you think the optimistic outlook looks like for the next 10 years of the technology.
I absolutely think it's going to be everywhere in 10 years, and not just moving data in supercomputers and data centers. We already have folks who are designing consumer devices, cell phones, laptops, who have the same problem getting data in and out of the chips that the data center folks are seeing. wanting to be able to use our optical I/O in cell phones. So I think
Oh, really?
everyone will be using this in 10 years, whether they know it or not. It'll help extend the battery lives of their phones.
Now we're talking.
There you go. And even beyond communication. So fundamentally, what our breakthrough does is it makes it possible to manufacture optics alongside electronics on the same chip. Communications is one place where it's useful to be able to use optics and electronics in a tightly integrated way, but it's not the only place. So this is a farther future-looking thing, but we're really excited about the impact that this breakthrough will have on all kinds of applications where light is used. For example, in sensors. Light is used as a sensing technology in a few different fields. LiDAR is a technology used in self-driving cars where a pulse of light is sent out and it bounces back, kind of like radar, except it's using light.
LiDAR? Oh, wow. That's pretty self-explanatory.
And so, maybe the level of integration that we offer will make an impact there in the future. Another place is in healthcare. Light is used for sensing in a lot of different types of healthcare applications. And right now, those devices are really big and expensive and bulky. And who knows what types of things we can create when you start integrating optics and electronics more closely for those types of purposes as well.
What about AR, VR, and things like that? I mean, obviously, there's tons amount of light. The things that you're looking at, whether it's Oculus or whether it's, anyone else, obviously, they're going to be using light. What are the applications for AR, VR, and things like that?
Yeah, definitely. There are some big ones. And most immediately, the need is just for more data movement between the headset and the rest of where you have your compute going on. I think even that issue that people have getting nauseous sometimes has to do with frame rate, and that has to do with data speed limitations that exist today. So even just using our connectivity system to get more data to and from that headset can have a big impact immediately. And then longer term, yeah, a lot of that does use light in various ways. So who knows?
What about just regular Wi-Fi? Because I feel like it's not fast enough.
So an annoying thing about light is you have to have line of sight, unlike with other types of wireless communications where, I could walk between your Wi-Fi transmitter and your laptop and you wouldn't notice it. With light, you would notice it because the light's not going through your body or through a wall. So there are some applications where it's okay, where, having line of sight is just fine, but it's not going to replace standard Wi-Fi.
That's really interesting. Let's get into the lightning round. This has been great, highly illuminative of what's going to be in the future, but it's time for the lightning round. Are you ready?
I'm ready.
So the lightning round is brought to you by the Lightning Platform by Salesforce. We're asking fast and easy questions, easier than the previous ones. First question, what app are you using on your phone that is the most fun?
Space Teams.
What is Space Teams?
It is my favorite iPhone game or Android, whichever platform you're on. It's a communal game that we play in our office all the time. It's how we initiate new members on our team as well. And you're flying a spaceship as a team and you're just throwing out absurd instructions at each other and having to listen to instructions at the same time. It's mass chaos and a lot of fun.
Oh, that's great. We're going to have to do that at the mission. That's awesome. What is your favorite time-saving tool?
I don't have any great answer here. I like Google Inbox. It saved me time in prioritizing things.
You'd be surprised how many times we hear calendar. Are you doing anything fun with AI or chatbots or machine learning? I mean, it's kind of just baked into the biz.
Yeah. We're not consumer facing, so we don't need, chatbots to talk to lots of customers about things. So yeah, that's not. We're more hoping to eventually improve those services through our hardware.
That's a great point. Favorite team, sports, or otherwise?
Can I pass on questions?
Yeah, of course you can pass on questions.
Passing on that one. I don't know, top of mind.
Your team? Maybe your team at Ayar Labs?
Oh, yeah, absolutely. By far my favorite team. That one's obvious, though. It goes without saying.
Touche. Favorite podcast that you've listened to recently?
I'm going to say yours.
I'll take it. Favorite book that you've read recently?
I haven't been a huge fan of my recent reads, so I'm going to go back to my all-time favorite, Cloud Atlas by David Mitchell. It's a fun combination of historical fiction and sci-fi all in one.
What's it about?
It's a collection of 6 short stories that are kind of loosely tied together. And I just love the kind of sweeping view that it has of tying different stories and people together through space and time. And its prediction of the future and its future-based stories are pretty crazy and cool.
I'll check it out. What's your favorite one-day getaway in the Bay Area?
I love just going to Rodeo Beach. It's not far at all. Marin Headlands. But it's beautiful. Hiking around there, swimming.
I have never been to Rodeo Beach. That sounds great. I'll have to put
recommend it. It feels like you're a million miles away, and it's so close to the city.
That's why I love Mount Tam.
That is beautiful, too.
What is your best advice for first-time CEO?
I would say you're going to get tons of advice from all over the place, especially when you start fundraising. Every investor you pitch usually has a lot of experience starting companies or working with startups, and they'll have tons of advice for you. And the hardest thing is figuring out how to wade through all that advice and what advice to take and not take. I would say if I were to talk to my younger self 3 years ago starting this company, I would tell myself, don't take all the advice too seriously. Try to pay attention to trends. If you're hearing the same advice over and over again, then that's probably important. But when it comes down to it, no one's ever done what you're doing before. And so no one knows what the right answer is. We're all figuring it out as we go along, and no one knows your company as well as you do. So trust yourself.
Love it. What technology, other than the one you're building, are you most excited about for the future?
Bitcoin. I really think we're at the beginning of something big. I think it'll be a while before we really see the impact it's going to have on the world, especially in places where people don't have a central bank or a currency that they can rely on, where they're seeing a lot of inflation, or where they don't have power necessarily over their own money, where a government could take it away from them. It's just incredibly empowering to people, and especially to women in countries where they don't have access to banking the way that we do here.
I couldn't agree more. And it is amazing when people say like, well, you know, nobody spends it here in America or whatever the use case that they say. It's like, well, first of all, it hasn't been around that long. And number two, go talk to people in other countries who are using it, who face those problems. Imagine if you couldn't take money out of your own bank and what that would feel like.
So I have to put a plug in for Roya Mahboob. I'm on her advisory board. This was the first female tech CEO of Afghanistan. Back in 2013, she decided to start paying her employees in Bitcoin because it's really tough for women in Afghanistan to have bank accounts. Yeah. And typically they need the approval of or permission of their fathers or husbands to be able to. And she wanted to pay them directly. So she did, and much later, one of her former employees ended up having to escape and seek asylum in Germany. She ended up still having access to her Bitcoins, and it helped her set up her new life there. So it's just such an incredible story that women were able to get paid in the first place, get employed in IT, and then just have control over their own money.
Couldn't agree more. That's it for the Lightning Round. That was it. Lightning Round is brought to you by the Lightning Platform by Salesforce, a leading cloud platform that makes building AI-powered apps faster and easier. Salesforce now building apps is everyone's business. Learn more at salesforce.com/build apps. That's it. Thanks so much for coming on the show, Alex. You are phenomenally generous with your time, and we really appreciate it, and we're excited to see what you and the team continue building. Any final thoughts?
This was really fun. Thanks so much for having me.
Yeah, thanks for coming on.
Thank you again to our friends at Salesforce. IT Visionaries is brought to you by the Lightning Platform by Salesforce, a leading cloud platform that makes building AI-powered apps faster and easier. With Salesforce, now everyone can build apps for their organization. Learn more at salesforce.com/buildapps.